So here's the last part of our notes for this lesson. And it's just, going over some other fun things like exponential functions. Here again is the presentation of the graph of what e to the x looks like. And I can kind of go over it here. The domain is all real numbers. There's a horizontal asymptote at y equals 0. That's reflected in the range down here. So this is f equaling e to the x. And the crazy thing is that it's its own derivative. That if I think about the derivative, it's the same equation. It's also e to the x. Okay, so that's kind of wild. Let's take a minute and think about it just for a second. Why is that? Why is the derivative of e to the x the same thing as itself, right? So let's prove it. You certainly don't have to prove this for me, but I just want to give some background on why things are the way that they are. So if y does equal e to the x, which it does, let's think about the strategy that we just worked on in the last little section here, which you can maintain equality by taking the natural log of both sides of an equation. That is possible. I can kind of work on what I have. The left-hand side is natural log of y. And what happens here, when you have a natural log up against an exponential base e, those are inverse functions of one another. They cancel. That reduces to x. So pretty crazy. I took an explicitly defined equation, right? That's clearly y equals e to the x. And I rewrote it as an implicitly defined function. Well, that means I can use implicit differentiation, people. So I'm going to do it. The derivative of the natural log of y is 1 over y dy dx. The derivative of x is 1. And if I want to get dy dx alone, which I certainly do, I'm going to multiply both sides of the equation by y. That's going to cancel out the y. So what I've just discovered is that dy dx equals y. And we know from that last piece of our video that it is not okay to leave your derivative in terms of the y variable if your original equation was explicitly defined there. Your original equation was all in terms of x. Your derivative should be all in terms of x. Then go ahead and make the swap. Y equals e to the x. So I've just proved why the derivative of e to the x is itself. Not your responsibility to do that, but certainly worth it. Okay, one thing to mention here, just on top of all of our characteristics, right, it is continuous, this graph is increasing, it's concave up. Just a nice ordered pair to note on the graph. I might as well put it on here. We did this for the natural log function, is that the exponential graph base e goes through 0, 1. I'm going to write that as a property just because it's nice to know. Just remember that e to the 0 is 1. You know that from basic algebra. A number to the power of 0 is 1. So it's just something nice to throw into the characteristics. All right. Now, let's get into our derivative rules, which again, once you learn the basic rule, they're going to always work the chain rule in here, that the derivative of e to something is e to that something, and then multiply by the derivative of that something. So we're going to execute these in a couple of different ways. And we're going to go through some basic derivatives, and then we're going to work on some more complicated ones. So I'm going to just start with the derivative, right? This is an exponential, dy dx. I can use that. I could use y prime if I want. The derivative of an exponential is itself, but I have to chain this because that's x over 2. The derivative of x over 2 is 1/2. Because let's think about it. X over 2 is really 1/2 x. Let's write that. X over 2 is really 1/2 x. So the derivative of x over 2 is 1/2. That's a good looking derivative right there. I think maybe I'll just take an extra little bit of time here and just, maybe I'll just throw it as a coefficient in front, just to make sure that I'm communicating my answer well. Okay, there we go. Question number 2. Function number 2. We can get started with the derivative. Of course, I will use the notation of f prime just because they gave me f, but this is a product rule, so let's get after that. It's going to be first unchanged times the derivative of e to the 3x, which is itself, and then chain it. And then I'm going to add to that the derivative of the first term times the second unchanged. I'll just regroup a little bit. Play around with it. That's 3x cubed e to the 3x plus 3x squared e to the 3x. That's a good-looking derivative. Be prepared for seeing something that might be factored out. So take out a GCF. 3x squared e to the 3x would be your GCF. So just be comfortable with recognizing that this is the same exact expression. Okay, it just looks different. Okay. All right, let's move on to some of these guys in here. And so we're just playing around with a couple of things that on a situation like question number 3, you do have some options. I'm not opposed to the quotient rule, so I'm going to use the quotient rule on this. QR for quotient rule. And let's get in here and do that. I'm going to use G prime, since this was labeled as G. And I always start the quotient rule with doing the denominator squared. We'll tackle that in a second. And then I'm gonna move on to that numerator. And again, order matters. It has to be bottom unchanged times the derivative of the top, and the derivative of tangent is secant squared, minus the top unchanged times the derivative of the bottom, which is e to the x. Now, I'm going to mess around with this a little bit and just change it up a little bit and see what happens. So what I see here is I have 2e to the x secant squared x minus 2e to the x tangent x all over e to the x squared. Well, that's e to the x times e to the x, right? So let's think about that. I can actually cancel one of those e to the x's. Now, I am going to factor out that common factor of e to the x. That's how I know this is a slashable moment, that yes, you can get in there and cancel one of the e to the x's. The other one's going to remain, okay, that's fine. But you have a simplified answer right here. Now, for those of you that are wondering, you certainly could, if you wanted to, I'll just change a color here, if you wanted to do this derivative as a product rule, oh, you certainly could. You should get an equivalent answer. You would just bring that e to the x up, and then it would have a negative exponent. You're probably used to that from Calc 1. Sometimes maybe your instructor did that. That would be acceptable and appropriate if you wanted to. In the interest of trying to be a little bit more efficient here, you can use the quotient rule on problem number 4. That would be appropriate as well. But I could avoid it, and I might as well do that for you. You know, if I can avoid the quotient rule, let's talk about it. You can break this down if you want. Let's just play around with this a little bit. Let me go back to blue, since I'm not going to be changing the equation. I'm just going to change the way that it looks. There's nothing saying you can't deconstruct this from its common denominator. So I have a binomial in the numerator and this 4e to the x in the denominator. Well, both of those things are divided by, both of those terms are divided by the 4e to the x. 12 is divided by the 4e to the x, and the e to the 3x is divided by the 4e to the x. So why not just do that? Like, let's split it apart and handle it term by term. I don't have to do the quotient rule. Great. Let's see, I'll reduce that. That would be 3 over e to the x. And this would be, okay, let's think about it. I have a 1/4. And I subtract exponents here when I'm reducing. So e to the 3x minus x is e to the 2x. This is great. Look what I got here. I got a new version of this equation that I used a little bit of fancy algebra and I've avoided the quotient rule. Let's do it. Let's actually now take the derivative. So I'm going to use that prime notation. The derivative of 3e to the x is, 3e to the negative x is 3 times e to the negative x. But I'm going to multiply by a negative 1 because I needed a chain. The derivative of negative x is negative 1. That's why that's there. Chain rule. Now I have this other term, the 1/4. The derivative of e to the 2x is itself, and then I chain that. So that's why I have an extra 2 flying around. Okay, so let's regroup. The derivative is negative 3 e to the negative x minus, let's just say 1/2 e to the 2x. Now, you might have had an instructor that said, oh, you have to have only positive exponents in your final answer. Okay, there you go. That looks great. If you want to, you could write this as a common denominator. That would be appropriate if you wanted to. If you see an answer that looks like this, just know that it's equivalent. Let's see, that would be minus e to the 3x. This is exactly the same derivative. Okay, just throwing that out there. Okay, so let's take a look at our next example, which you can see I've got a lot of space here. So let's think about it. This is an equation that is jumbled up. Right? I've got x's and y's all jumbled. I do not have an explicit function y being defined in terms of the x variable. This is implicit differentiation. I'm going to label it. So we're doing implicit differentiation in the context of exponential base e. So let's do it. I am going to start just by taking the derivative. The derivative of 3e to the x over y is itself. Now remember, I have to chain that. Let's really pay attention to this. I'm going to maybe use the quotient rule. Why not? That'll work. I can mess around with that idea. Okay, so let's do it. Let's take the derivative of x over y. What would that look like? Well, it would be over y squared, and I would have bottom times the derivative of the top minus the top times the derivative of the bottom. That was me just chaining out the x over y. The derivative of negative 6x is just negative 6. Okay. And over here, the derivative of 10y is just 10 dy dx. Okay. So let's get in here and try to clean this up a little bit. This looks like a complete disaster of a lot of work, right? So let's think about it for a second. Let's try to reduce that down and play around with what it is that we have. Okay, so if I work on that particular idea, I think what I'm going to do to try to make my life a little bit easier here is I think I'm going to multiply everybody in this expression by y squared. Why not? I want to get rid of that fraction, right? That dividing by y squared. That's what's making this look so complicated. So here's what I'm going to do. I'm going to multiply everybody in this expression by y squared. Everybody gets hit. So let's do it. What that's going to do in here, it's going to knock out the denominator. Okay. This was one giant term being multiplied. If I multiply by y squared, it kind of cancels out that y squared in the denominator. But I have to hit it up by this term. And I have to hit up that y squared in the last term. So just different algebraic strategies here. I just wanted to tone it down a little bit, get rid of the quotient part. So I've successfully done that because I've multiplied every term by y squared, so I maintain that equal sign that I want to preserve. I have to separate the dy dx's from everything else, but I'm not ready yet. I don't see them all term by term. This 3e to the x over y is multiplying that binomial. So let's address that. Let's actually work that in. Let's get that all cleaned up. Okay. I'm going to rewrite the rest of my terms. Now I'm actually ready to play the game of haves and have-nots. Let's put all the dy dx's on one side. Let's put all the non-dx dy dx terms on the other side, whatever that means. And so we'll play around with it. And again, you could do whatever you want. I think I'm going to move everything over to the right-hand side, all the dy dx terms. So this guy is now going to hop over and become positive. What stays over here is the 3y e to the x over y and the minus 6y squared. So once again, the reason I separated those is to recognize the GCF over here of dy dx, which is exactly what I'm trying to get by itself. That's the entire point to all of this. So I will preserve that. Let's just write it, dy dx. And that is all multiplying. What would I have left over? 3x e to the x over y plus 10y squared. I didn't do anything over here on the left-hand side. I'm just rewriting. But here I have a clear path forward of how to find that dy dx. I'm just going to divide whatever is multiplying that dy dx. So there it is. So dy dx happens to be equal to 3y e to the x over y minus 6y squared over 3x e to the x over y plus 10y squared. So that is my derivative. And it is appropriate, it's okay to leave my derivative with the x's and y jumbled. Because once again, our original equation had x's and y's jumbled. So that's okay. This is implicit differentiation. That's naturally going to happen. Okay. Here is our last example that is worth our time. And you can see it's a heavy hitter. It's everything we've talked about in this lesson all thrown together. So let's do it. I am going to take the derivative implicitly because that is really my only path forward. However, I can use a little bit of strategy here. You've got a natural log. I don't know if you see that there, but that is a natural log. Let's go ahead and use our properties. Let's do that. That I don't have to leave it here where I'd have to do a chain rule with implicit. No, what I can do is break that up. That is the same thing as the natural log of x plus the natural log of y. And yes, there are more terms, but that is easier to take the derivative. So let's now finally say, okay, now I'm ready to take the derivative. The derivative of 1 is 0. The derivative of the natural log of x is 1 over x. The derivative of the natural log of y is 1 over y, and then I'm going to slap that dy dx on it because it was a y variable. And then over here on the right-hand side, that's an exponential. So I'm going to do it. The derivative of exponential base e is itself. I just have to make sure that I chain it. So the derivative of x is 1, and the derivative of y is 1, but I have to slap that dy dx on it. There we are. Now, I'm going to play around with this. So I don't need the 0 there. That's silly to rewrite. I'm not really doing anything fantastic over here on the left-hand side. However, I do want to notice here that you have this one term multiplying a binomial. So let's go ahead and do that so I can see these individual terms instead of being in that factored form. So 1 times e to the x minus y is just e to the x minus y. And then when I distribute it, I would have negative e to the x minus y dy dx. That allows me to write it in a way that I can see all the individual dy dx terms. Now I can separate my equation into dy dx terms and non-dy dx terms, right? The haves and have-nots. So just to be, I don't know, flexible, I'm going to now say, oh, let's move all the dy dx's over to the left. Why not? It doesn't matter which side you move them over to. So that means I'm going to leave the 1 over y dy dx already here. I'm going to move this guy over, and it now is positive. Dy dx. And now I'm going to leave that e to the x minus y, but move that 1 over x over. It becomes negative, right? And so once again, this is implicit differentiation. I have arrived at a good spot. I've got everything with a dy dx on one side of the equation. That is now like you're basically factoring like algebra 1. You're taking out the GCF. And that is exactly what I'm going to divide by. I want to get this thing to say dy dx equals, you got it. I'm just going to divide by whatever is multiplying that dy dx. Now, you can see math people do not like this expression. You have fractions and fractions. That is a problem. It is a solvable problem, and it's a quickly solvable problem. Let's look at those two denominators that I've got. You know, the denominator of x, we don't like that. The denominator of y, we don't like that. I want to get rid of the complex fraction in one shot, really efficiently, really quickly. And remember, you can always multiply an expression by 1 and not change its value. So let's do that. So I'm going to multiply everybody by x times y. That's a really creative way of writing 1. If 5 over 5 is 1, well then xy divided by xy is 1. I'm choosing that to make my life easier. Now I'm going to multiply everybody by x times y. So that means your first expression here gets a little bit uglier. However, here I have that minus sign, right? I'm just carrying that through. Here the x's cancel. I'm just left with minus y. Complex fraction annihilated. That's the whole point. Now, in the denominator, right? So I carried it through to both of the terms in the numerator. In the denominator, that's what's going to allow you to cancel out the y. What do I have left? An x. And then your next term gets a little bit bigger. You have to say, look, I did multiply the e to the x minus y by x times y as well. There is your good looking derivative that all math people like. Okay. All right. So thank you so much. And that is the end of our first lesson.